All right, so problem 9, we see x to the fourth minus 144. We're supposed to rewrite the expression as a product of two binomials. We haven't done x to the fourth yet, but when I look at it, I notice that this looks awfully familiar. X to the fourth is a perfect square of x squared. 144 is a perfect square. We're subtracting two perfect squares, which makes this a difference of perfect squares. How do I do a difference of perfect squares? Well, we knew what we would do if this was x squared minus 144. So why would this be any different? We're going to take the square root of the first term. So square root of x to the fourth is just equal to x squared. The square root of 144 is 12. We know it's binomials, so we're going to have two binomials, so two sets of parentheses. We know our first term is going to be x squared in both. We know 12 is our second term in both of the binomials. And we just remember it's plus and minus. That's why the middle term, the bx term, goes away. So now we just have to enter this in. I'm going to start by entering in parentheses, x, and this button right here, the box with a little bit of a box above it, will give us our exponent, x squared. I have to hit the arrow key to get out of the exponent again, plus 12. So hit the arrow key to get out of the parentheses, start a new set of parentheses. Again, same thing, x, exponent squared. Now we do minus 12 and close that off with the parentheses, and that is our equation, and that is our answer. In this equation, we're given a linear equation, and we're asked to write a linear function g of x such that f of x equals g of x has exactly one solution. What is the exact solution to f of x equals g of x? Well, if we create another linear function g of x, it's only going to cross f of x once. Now, there's a lot of ways we could do this. We could come up with a different slope and all that, but let's remember, the only way two linear functions will never intersect is if they're parallel. And for linear functions to be parallel, they would have to have this identical slope and a different y-intercept. So as long as they have the same slope and a different y-intercept, they'll never touch. Otherwise, every other equation with a different slope will go through this. Now, one other thing was we know the y-intercept of this equation. Again, that's pretty straightforward. It's negative 0, 0, negative 3. But just in case we're not sure, oops, wrong button. That's our original equation there. Just to confirm it, we have a y-intercept at 0, negative 3. You know what else has a y-intercept at 0, negative 3? This equation, y equals x minus 3. They both have a y-intercept of 0, negative 3, which means they both have a solution when x is equal to 0. This is about the easiest equation you can do. They have different slopes. They have the same intercept, which means they will intersect at the same point. We could have made it any slope. We could have made this 150x if we wanted to, and they would still intersect at this point. We could have made this 7 divided by 2, and they would still intersect at the same point. It doesn't matter. So when we go back to our equation, we're just going to type in the very simple x minus 3. And then since they're intersecting at the y-intercept, our x value for every y-intercept is 0. And that's a pretty easy solution. All right, for problem 11, we're given a quadratic, and we're asked for which interval of t values is the function both positive and increasing. Well, we have to realize that it's going to be positive, so we can automatically rule out A. A says for t less than 5. Well, values less than 5 would include negative numbers, so A is right out. Okay? So now we're looking at t between t greater than 8, t between 2 and 5, and t between 5 and 8. Easiest thing to do is go put this in your calculator. I've put in the calculator. I went to the gear button, and I'll show you what I did there. I went to the gear button here, clicked it, set for table, and what I notice is this function will increase until the vertex, which is right here. Notice my x value is at 5. My function will continue to increase until 5. So that means after t equals 5, it's decreasing, so the greatest value I can have is 5, which basically gives us our answer already. But just to confirm, as I look at this, I see my function is increasing all the way up here until x equals 5. When I have x equals 6, it starts to decrease. My y value goes down. However, at t is 1, 0, -1, -2, all of those values for t less than 2, our y values are negative. So we look at it from t equals 2 to t equals 5, our y values are positive. Again, 2, 0, 3, 5, 4, 8, 5, 9. Those are all increasing. So our answer for this one has to be t is between 2 and 5. All right, in this equation, we're asked to create an equivalent expression in the function of the form f of x is equal to x minus h quantity squared plus k. We're told two key pieces of information. In the first one, we're given the function x squared plus bx plus 144. We're told that our y-intercept from this is 0, 144. That's what happens from your standard form. Your c value is your y-intercept. We're then told the minimum value of the function is 80. That means our lowest y value is 80. Well, as you remember before, for a quadratic function, either we're going to have a minimum or maximum, and regardless of which one we have, it's our vertex. So we know our y value of our vertex is 80. And we know we have to go through a y-intercept of 144. We also know that 80 is the k value in vertex form because it's part of the vertex. Our vertex is hk, and we're going to put that back into our vertex form of the equation, which is right here. So I'm going to construct a function, y equals x minus h quantity squared. I don't know what h is, but you'll see how I can figure that out in a moment, plus 80, because I know my vertex is going to be somewhere at y equals 80. Now I'm going to zoom out here, and I'm going to add a slider for h. And what we'll see as I zoom out here, and I'm going to reorient my zoom here, is that I have a vertex. Well, that's not my vertex, of course. That is the y-intercept. But I can see here that I have a vertex at 180. Okay? So this would be if my vertex was at 1. But however, the other thing we have to do is we have to find our y-intercept of 0, 144. I could create a table here. And again, I see 0, 180, 0, and 81. So I'm going to change my h value by moving this button here. And I'm going to do so until I find the point 0, 144. And you'll notice my function, or my graph, also shifts as well. As I continue to do this, I see that I'm getting closer to 144. Getting closer, closer, closer. And finally, at h equals 8, I see I have a y-intercept at 0, 144. So my function then would be x minus h quantity squared plus 80. This is the simplest way to solve this problem. So I go y is equal to, or f of x would equal to 8x minus 8 quantity squared plus 80. Now, algebraically, I could solve this problem. I know that when x is equal to 0, y is equal to 144. And what I could do, I'm going to clean up the old problem there, is I could say 0, or sorry, not exactly what I wanted to do. I could say that since I know my y-intercept is 0, 144, I could say when my y value is 144, x is equal to 0, and what that would give me is 144 is equal to 0 minus h quantity squared plus 80. I'm using my mouse pad for it, so it's a little bit hard to draw. And then at that point, I'm going to get 144 is equal to h squared. Think about it. If you have negative h and you square it, it's going to be positive h squared. It's equal to h squared plus 80. At that point, you just subtract 80 from both sides, take the square root of both sides, and you're going to get plus or minus 8. Either of those solutions would actually work. Let's go on to problem 13. All right, we're told G and H are integers that satisfy the following conditions below. Those are going to be positive whole numbers, such that G and H are between 1 and 10, with G being smaller than H. We're told that the square root of G plus the square root of H is irrational, and we're told that the square root of G times the square root of H is rational. And we're asked to find out the values of G and H. So we have to understand a couple things. An irrational number is a number or value such that its decimal can't be expressed as a fraction, nor can its decimal be expressed as something with a repeating decimal, nor is it a whole number. Now, if I'm summing two numbers together, which the square root of G and the square root of H are, and I get that that's irrational, that implies that both G, the square root of G, and the square root of H are both irrational. That means that the square root of G and the square root of H cannot be perfect squares. Perfect squares would give me a whole number, which would be rational. If I know my numbers are between 2 and 9, I know that 4 and 9 cannot be options because they, of course, are perfect squares. Now, the next part says that the product of the square root of G and the square root of H is rational. If it's rational, then that means that it's probably going to be a perfect square. So now we have to figure out what combinations of numbers between G and H, or G multiplied by H, would give us a perfect square. So let's start off by going through these numbers. 2 times 3, that's equal to 6. And we know 6 isn't a perfect square. 2 times 5, that's 10, so that's not going to work. What about 2 times 6? That's equal to 12. That's not going to work. What about 2 times 7? Well, that's 14. That's not a perfect square. What about 2 times 8? Well, 2 times 8 is equal to 16, which is a perfect square. After all, the square root of 16 is equal to 4. So 2 and 8 would be a possibility. I could go through the rest of them. 3 times 5 is going to be 15. 3 times 6 is 18, not a perfect square. 3 times 7, 21, not a perfect square. 3 times 8, that's 24, not a perfect square. 5 times 6 is 30. 5 times 7 is 35. 5 times 8 is 40. None of those are perfect squares. 6 times 7 is 42. 6 times 8 is 48. Not perfect squares. 7 times 8 is 56. None of them are perfect squares. So our values must be 2 and 8. G is smaller than H, so G is 2 and H is 8. All right, finally in this problem 14, we're given a function f of t is equal to negative 16t squared plus 20t plus 4. That gives the height of a ball in feet 10 t seconds after it's tossed. This is a quadratic. We're asked to find the average rate of change in feet per second over the interval 0.75 to 1.25 seconds. This requires us to put this in the calculator. All right, I've put this in the calculator. I've created a table by going to gear, hitting this gear button, which is edit list, and selecting the table. I need to find the output values for x is 0.75, where it's 0.75 seconds, and at 1.25 seconds. And I find that those output values are 10 and 4. The key takeaway from this table, and to remember, is that when we're asked for rate of change, we're basically asking for slope. We see that from the points brought up, we're basically going to have a negative slope or decreasing. So our slope formula, m is equal to y2 minus y1 over x2 minus x1. These are our ordered pairs from the graph, labeled x1, y1, and x2, y2. And when we plug them into the formula, we get 4 minus 10 over 1.25 minus 0.75. That's equal to negative 6 divided by 0.5, which is equal to negative 12. So our rate of change here is negative 12.